Hello friends, in this course on radiative heat transfer, so far we have discussed radiative heat exchange between surfaces and bounded by vacuum. So, what we mean by participating media that we are going to discuss in this lecture is that when radiation travels from one surface to another, the medium which may be gas, particles may interact with the radiation. Now, interaction may be of multiple forms. The radiation may be absorbed by the media, radiation may be scattered, or the medium itself may emit radiation and augments the intensity of radiation. So, the analysis of this type of problem where we have participating media is going to be much more challenging and interesting as well. Although the problem of radiative heat transfer between surfaces without any media was complicated enough, but together with this participating media, the analysis is going to be much more difficult and the analytical solutions would be very difficult to obtain. So, most of the models that we will discuss in this course will be approximate models, and we will also introduce some numerical methods to solve problems including the participating media. So, the participating media, the problem is very interesting. We see a number of applications where we have gases and particles that absorb and emit radiation. For example, we have spacecrafts. In spacecrafts flying at high altitudes or returning from deep space missions, the velocity is very high. The velocity may be in kilometers per second, and the spacecrafts are subjected to extremely hot environment. This leads to ionization and dissociation of gases at very high temperature. Radiative heat transfer is the dominant mode of heat transfer in this case. Similarly, we have fires, the flames and combustion applications where we have different type of gases and particles radiating. The white color basically comprises of wavelengths of different wavelengths, while we have typical yellow flame because of radiation coming from soot particles. So, soot particles are basically small carbon particles which radiate energy like black body, and the radiation that appears from these type of flames which we have soot content will be yellowish in nature. We call it luminous flames. On the other hand, there are some flames which appear blue in nature. Now, the color from these flames is a result of some radicals of methane and carbon monoxide and some other compounds like C2 which have bluish and greenish color of the flame. We also find participating media in atmosphere where solar radiation travels through clouds, water vapor, suspended water vapor in the atmosphere and other gases. So, this radiation, solar radiation is absorbed by the atmosphere as well as it undergoes scattering. So, all these problems require modeling of participating media in radiative heat transfer. So, there are as I said, the medium, the participating medium may absorb radiation, it may scatters radiation as well as it can lead to increase of intensity by emission. So, large number of applications find radiative heat transfer in participating media such as combustion, rocket propulsion, hypersonic shock layers, ablation, fusion reactors, and also in atmospheric sciences. So, we start by looking at the solar spectrum, because solar spectrum is most widely studied topic in radiative heat transfer in participating media. So, if we look at the solar spectrum, outside the Earth's atmosphere, that is extraterrestrial solar spectrum as received from sun, but not encountering the atmosphere, the solar spectrum behaves like a black body, okay, at 5770 Kelvin, okay, and the total heat flux that we receive and on top of the atmosphere is 1367 watt per meter square. Now, this radiation is extraterrestrial, it is not subjected to absorption and scattering by molecules and particles in the atmosphere. When the same radiation penetrates our atmosphere, it is subjected to absorption and scattering by a number of gases, and the most important gases that absorb solar radiation are basically water vapor and carbon dioxide, which are in major amount in our atmosphere. So, we see that the radiation is absorbed, that means the intensity of this solar spectrum does not follow anymore the black body spectrum. We find that the intensity has decreased at a number of wavelengths. The wavelength on the x axis is in microns. Okay. So, the significant absorption we find is in ultraviolet, which is due to ozone. We all are familiar with ozone layer that absorbs harmful ultraviolet radiation. Then in infrared we have mostly this is infrared region, where water vapor is important gas that absorbs solar radiation, and then we have absorption by oxygen molecules and carbon dioxide as well. The one thing that you should observe here is that the absorption is not uniform throughout the spectrum. Somewhere the absorption is high, somewhere the absorption may be low. These type of absorption pattern are called bands. Okay. So, each absorption pattern is basically called a absorption band. Okay. And we will discuss, when we discuss the molecular radiative properties of molecular and atomic gases, how these bands basically are formed, but one should keep in mind that the absorption by gases is not uniform. It is centered around certain bands, and these bands for the solar spectrum are located in visible and infrared region, while ozone absorbs radiation in the ultraviolet part of the spectrum. Lot of interest has been in the transmissivity of carbon dioxide, which is a major pollutant also in a large number of combustion applications. So, CO2 has been of great interest not only in atmospheric sciences, but also in combustion, because carbon dioxide is a major absorbing gas of radiation in atmosphere where the temperature is low, but as also in combustion where the temperature is high. So, lot of measurements, experimental studies have been done on CO2 transmissivity at low and high temperatures, both low resolution and high resolution. In this plot taken from Modest and Bhardwaj, the x axis is in wave number. This is another way of representing the color or wavelength or the frequency. So, wave number, and on the y axis is the transmissivity, and again we see that there are certain bands of CO2 which have low transmissivity value and certain bands which have high transmissivity value. Now, the plots obtained or plotted in this figure have been taken, the data for these plots have been taken from a number of standard resources like HiTemp and HiTran 96. These two are databases which have large number of spectral data, that means information to calculate the transmissivity of the gas at the function of wavelength. The data has been collected by a number of researchers over a period of many years at different resolution, different temperatures. The data contains both experimental as well as theoretical data. So, we will see how this data can be used to calculate the properties of gases, not just CO2. The database has large number of gases, and we can calculate the transmissivity of these gases using this database. So, we start our analysis of participating media with the well known law, Beer's law. So, Beer's law says that when a radiation of photons enters a medium, it undergoes exponential decay, and this exponential decay depends on two quantities. One is the length of the path travelled and the property of the gas kappa lambda, that is called absorption coefficient. So, amount of energy absorbed within the medium depends on the path travelled and the absorption coefficient of the medium. Okay. So, the transmissivity is defined as exponential of minus kappa lambda s, where kappa lambda is the absorption coefficient and s is the path travelled. So, this is the Beer's law, and similarly similar to the properties of surfaces, the absorptivity, that means amount of radiation absorbed by this gas layer, is defined as 1 minus transmissivity, which is 1 minus exponential minus kappa lambda s. So, Beer's law has found many applications in chemical engineering, where the concentration of solution is found by passing some radiation through a solution, and based on how much radiation is absorbed by the solution, one can calculate the concentration of the solution. So, for a detailed analysis of radiative heat transfer in participating media, we will develop the equation of radiative transfer. So, equation of radiative transfer basically tells how the intensity of a single wave travelling within a solid angle, small solid angle d omega, undergoes emission, absorption and scattering. These three modes basically alters the intensity of the radiation as it passes through space. The variables in this problem, we have total 7 variables in this problem. The intensity will vary in space as a function of x, y and z. The intensity also depends on two angles, polar and azimuthal angle, as we have already discussed, and it is a function of wavelength and also time. So, intensity at two location, let us say S1 and S2, the distance between S1 and S2 may be of the order of meters. For typical combustion applications, it may be of the order of kilometers. If you are talking about atmospheric sciences, the time requires for radiation to reach from S1 to S2, but there are certain applications, as we will see, where time may be a parameter, an important parameter, especially lasers of femtoseconds and nanoseconds, where transient radiation modeling may be of importance. Before we start writing the equation of radiative transfer for participating media, we recapitulate the definition of intensity. So, radiative intensity is basically defined as energy transferred per unit time, per unit solid angle, per unit area normal to pencil of rays, and spectral intensity also has per unit wavelength. So, this is the definition we have already discussed, and we will see how this intensity changes over space and time. Intensity in vacuum, because in vacuum there is no participating media, so intensity will remain constant. The intensity will not suffer absorption, the radiation will not suffer emission from any gas or particles, and there will not be any scattering. So, under the absence of participating media, the intensity will remain constant, while in participating media the intensity will continuously change in space and time because of these three factors: absorption, emission and scattering. So, we will take these factors one by one. The first one we will take is absorption and scattering. Now, absorption and scattering may lead to attenuation or decay of intensity. So, intensity will decrease because of absorption and scattering. Okay. So, in this schematic you see that a large number of photons are travelling through this medium, which has thickness ds and cross section area dA, and the direction is s. Now, when these photons encounter participating media, some of the photons are absorbed within that medium and some photons are basically scattered. So, these photons are scattered away. So, this definitely will result in decrease in intensity, and some photons are basically absorbed within the medium, and definitely this will increase the energy of the medium. So, absorption of radiation within a medium will increase the internal energy of the medium, and the intensity will decrease. So, we define change in intensity d I lambda due to absorption. So, d I lambda is change in intensity due to absorption. So, we will write separately change in intensity d I lambda for absorption and scattering. So, this is proportional to the incoming intensity and the path travelled ds. So, the change in intensity of radiation when it travels through a small path ds depends on the incoming intensity, and we can replace this proportionality sign with a constant. This becomes kappa lambda I lambda ds. So, change in intensity of radiation as it passes through a small participating media of thickness ds is equal to minus kappa lambda I lambda ds. Kappa lambda is defined as linear absorption coefficient, which is a measure of attenuation. Now, in many combustion applications as well as in atmospheric sciences, linear absorption coefficient is not preferred. So, in these areas mass based absorption coefficient is preferred. So, mass based absorption coefficient is nothing but kappa lambda is equal to kappa rho lambda times rho. So, the units basically we have changed, we have added another parameter to define the absorption coefficient. Similarly, there is a pressure based absorption coefficient we can define as kappa p lambda times p. Okay. So, this is pressure based absorption coefficient. So, when you are dealing with the different type of absorption coefficient, you should keep in mind the units of the absorption coefficient, because the units of linear absorption coefficient is different than pressure based absorption coefficient, and when we are using pressure based absorption coefficient you have to multiply by the pressure of the medium. We can integrate this equation, and we find that I lambda s is equal to I lambda 0 and exponential E minus tau lambda, which is seen as the Beer's law. So, intensity, this is the intensity I lambda 0 and this is the intensity I lambda s of path s. Okay. So, it follows an exponential decay as has also been observed by the Beer's law. Now, we have used integration here because the property kappa lambda may be a function of x or it may be uniform. So, kappa lambda absorption coefficient may continuously change over the path or it may be uniform. If it is uniform, we can take it out of the integral, and integral 0 to s kappa lambda s will be simply equal to kappa lambda ds. Okay. And then it will be simply equal to I lambda 0 e to the power minus kappa lambda delta s. Okay. So, we have used integration here because we are making a general derivation. So, we assume that kappa lambda may also vary with the coordinate. Okay. So, this quantity tau lambda, now please bear in mind this tau lambda and this transmissivity we define in the Beer's law is not the same. Okay. The tau lambda here was transmissivity, okay, while the tau lambda that is defined here 0 to s kappa lambda ds is not transmissivity, it is optical thickness, okay, optical depth or optical path length. This is basically a non-dimensional number which we find by multiplying the absorption coefficient with the path length. Okay. So, this thing many times you may get confused for the same use of symbol, but tau lambda here is optical depth or optical thickness. Now, attenuation by scattering is very similar to attenuation by absorption. We may have radiation coming from certain direction, it may encounter some molecule or some particle, and the energy may be scattered in different directions. The directional dependence may be different. Some particles tend to scatter more radiation in the forward direction and less radiation in the backward direction. Some particles or molecules tend to scatter more radiation in the forward backward direction and less radiation in the forward direction. Okay. So, the point is that when a ray of radiative and photons, when in radiative path encounters any particle or gas and undergoes scattering, its intensity will change, and this intensity will change according to the same relation d I lambda scattering is equal to minus sigma lambda I lambda ds, where we have defined this coefficient, the proportionality constant, as spectral linear scattering coefficient. Just like we defined kappa lambda as spectral linear absorption coefficient, this is defined as spectral linear scattering coefficient. A quick note, although we will be dealing with the scattering in detail in later chapters, there are many type of scattering that we encounter in normal applications. The three common types are Rayleigh scattering, Mie scattering and Raman scattering. There may be other type of scatterings. Now, scattering can be elastic or non-elastic. Elastic scattering means that the photon does not lose any energy after scattering. Inelastic scattering means the photons lose energy after scattering. Okay. So, Rayleigh scattering and Mie scattering are elastic type of scattering where the energy of the photon is not changed, and when the energy of the photon is not changed during scattering, the wavelength of the photon is not changed. Okay. So, they preserve wavelength. So, atmospheric radiation, in atmospheric radiation we have molecules of water in the atmosphere, and these molecules scatter solar radiation. This type of phenomena is called Rayleigh scattering, and it gives blue color to the sky. The molecules are of very small size. So, small particle scattering or small molecule scattering is Rayleigh scattering that we have application in atmospheric radiation. In combustions we have scattering by soot and ash particles, especially in coal fired boilers. There we have scattering by large particles, relatively large particles, and we call it Mie scattering, and it finds application in boilers where scattering by particles blocks the radiative heat transfer, and it does not allow boiler surfaces to get heated from combustion gases. Okay. So, it reduces the heat flux and reduces the efficiency of the boiler, but scattering, as I said, redistributes the energy in all the directions. So, with scattering you will find generally more uniform temperature distribution. The gradients in temperature will be much severe when scattering is not there, while the gradients in temperature will be much less when scattering is there, because scattering basically acts to redistribute the energy in different directions. So, we combine absorption and scattering into a single coefficient. This coefficient is called extinction coefficient, which is sum of linear absorption coefficient and linear scattering coefficient. Beta lambda is the extinction coefficient, and we also can define scattering optical depth, optical path length based on this extinction coefficient as 0 to s beta lambda ds. So, these were two physical phenomena that leads to attenuation of radiation. Now, there are two phenomena that leads to augmentation or increase in intensity. The first one is emission and the second one is scattering. So, we discussed in the first lecture itself that all substances emit radiation, solid surfaces, liquids as well as gases. So, when a radiation ray passes through a medium, the medium itself will emit some radiation, and this radiation will basically adds to the ray and total intensity may increase. So, we write the increase in intensity d I lambda due to emission, which depends on path length again, and it also depends on the energy content of the medium, which is generally given by the black body function or Planck function I b lambda and the absorption coefficient kappa lambda. So, the total amount of energy emitted and due to which the intensity of the radiation a single ray changes is equal to kappa lambda I b lambda ds. Now, we can assume that scattering is not there. If we assume that the scattering is not there, we can combine the absorption and emission part and just write down the simplified energy equation or radiative transfer equation. So, this is his radiative transfer equation. For absorbing and emitting medium. In this there is no scattering, so scattering part is not there, but we want to derive a general expression for absorbing, emitting and scattering medium. we can integrate this equation as we did for the simply absorbing medium. So, we have intensity coming in from the left hand side, let us call the intensity is I lambda 0, and intensity going out, and this path length is S. So, it will increase due to emission. This is the term emission, where I b lambda is the Planck function and 1 minus e power minus tau lambda is the emissivity. So, this is the emission part or augmentation part, and this is the attenuation part or absorption part. So, intensity will change due to absorption, it will decrease due to absorption, and it will increase due to emission. Okay. If only emission is considered and absorption is not there, we basically assume that there is no intensity coming in. If we assume that, then the emissivity can be defined as I lambda S over I b lambda is equal to 1 minus e power minus tau lambda. So, this is defined as emissivity of gas layer. So, this is amount of energy emitted over certain path in a given direction. So, this is the emissivity, spectral emissivity. Now, augmentation by scattering. Now, scattering is a complicated topic. So, here we have basically, let us say we may have a single particle and radiation comes and strike this particle, and as a result it may scatter in different directions. Okay. The magnitude of scatter may be different in different direction. Okay. If it is uniformly scattered in all direction, it is called isotropic scattering, or it may be non-uniform, more forward scattering, less backward scattering. Okay, and there may not be side scattering at all. Okay, this is called anisotropic scattering. So, for our interest, let us say we have a radiation ray coming from certain direction S I within a solid angle d omega I. So, total amount of energy within this ray is, as per the definition of intensity, I lambda S I projected area times solid angle times the small wavelength. So, this is the total amount of energy coming from a certain direction. Now, out of this, the energy absorbed within this medium. So, this intensity strikes here and scatters in all the direction, and some amount of it travels in this direction. This direction is S, and the amount of energy absorbed due to scattering is simply sigma S lambda I lambda, the intensity dA d omega I d lambda ds. So, this is the amount of energy is scattered and absorbed within that path of thickness ds. Now, as I said, scattering occurs in all direction. If it is uniformly scattered, it is called isotropic scattering, otherwise it is called anisotropic scattering. We define the behavior of scattering using a function called scattering function or scattering phase function, phi lambda. Now, phi lambda is a scattering phase function which depends on two directions, which direction the radiation is coming from S I and which direction the radiation is going S. If it is independent of S, then it is isotropic. Okay. So, phi lambda is the scattering phase function. So, out of all the energy scattered, let us say this fraction is amount of energy scattered in a given direction S, because we are writing radiative transfer equation for this direction S. So, we want to know how much radiation coming from a certain direction S I is actually scattered and adds to the intensity in direction S. So, this is the fraction of radiation that is basically coming from certain direction S I and adds to the intensity in direction S. So, with this, the amount of energy from cone d omega I is scattered into the cone d omega, that is radiation coming from this direction and scattered into this direction will basically leads to increase in intensity, and this can be written by this expression. Now, we want to basically include all the directions. Okay. So, this is the direction of radiation coming in and going in this direction, we want to include all the direction. So, how much radiation coming from this direction is going into this direction, how much radiation coming from this direction is going into this direction, and so on. So, we want to integrate this expression over the entire solid angle 4 omega. Okay. So, please note the solid angle in this case, because this is we are dealing with space. This is not a surface where the solid angles will be limited to 2 omega. Here the solid angle will be limited to 4 pi, the entire solid angle we have to take. So, we integrate over the entire solid angle, and once we do that, we get the intensity augmentation, that is increase in intensity due to in scattering. This is called in scattering because radiation coming from certain direction is in scattered or scattered in the direction S. Okay. So, this is the expression for the augmentation by scattering, and we have an integration appearing into this expression, and this basically is the problematic part which makes the radiative transfer equation as integral equation, integral differential equation, and we will see how this basically appears in the equation. Because the energy is conserved, so the total integration of this scattering phase function should satisfy the energy conservation law. So, amount of total energy scattered in any direction integrated over all solid angles should be equal to 1, and for scattering, isotropic scattering, the phase function is simply equal to 1. So, most of the time we assume that the scattering phase function is isotropic or phi lambda is equal to 1, otherwise the calculations may be difficult to carry out. So, thank you. We basically in this lecture started some basics of radiative heat transfer in the participating media. We will carry forward the derivation of radiative transfer equation and solve some problem, and look into the cases of special interest for participating media in the next lecture. Thank you.